Hi, and welcome to Allen High School's discussion of the properties of substances, both pure and then we'll be moving into mixtures that are dependent upon their bonding and intermolecular forces. And so let's move into, we've been talking about phase changes. We're now going to talk about a few other properties. The first is vapor pressure. If we have a closed container, so even in your water bottle with the lid on, this is absolutely true. We saw this back, do you remember when we did that ideal gas law lab and we had to take away the vapor pressure of water? So you've seen vapor pressure. I want to refresh our memory. So this is simply a mercury manometer here. So as gas is formed, the gas is going to push with force. That's the pressure. Put a pressure or force on the mercury and the mercury will shift. So if I started with an evacuated container here and put a liquid in here, or maybe a container of known pressure and added a liquid in here, then the liquid's going to vaporize and form a gas. Now, eventually, we're going to reach a point, so that's why the mercury is moving. Eventually, you're going to reach a point where a gas molecule condenses every time a gas molecule vaporizes. So at the point at which the rate of going to liquid is equal to the rate of gas going to, the rate of liquid going to gas equals the rate of gas going to liquid. So when those rates, let's call that forward, is equal to the rate reverse, that's called an equilibrium. It's got to be a closed container for this to happen. And it's dynamic. It's a dynamic equilibrium because everything doesn't just stop. There's still condensation going on. There's still vaporization going on. But because the rates are equivalent, the pressure becomes constant. And at that point, we call that the vapor pressure of the liquid. And so we could measure that as millimeters of mercury, which, if you remember, is equal to a torr. That's where millimeters of mercury came about as a unit, is based on the height of a mercury column. All right, now, how does that link to intermolecular forces? Well, as the intermolecular forces or bonds, if it was a bonding situation, we're not really talking about that as much, but it would certainly hold true. As intermolecular forces increase, like we're comparing two different molecules, maybe a large molecule with London dispersion and a small molecule with London dispersion, or dipole-dipole molecule to something that hydrogen bonds, or that type of thing. But as intermolecular forces increase at and we're staying at a set temperature, fewer molecules escape to the gas phase. And so the vapor pressure will decrease. So another way we could write this is as you increase the strength of the intermolecular force, you're going to increase the moles of gas that form because you have to break an IMF to get to the gas phase. If it's a strong IMF, it's hard to break it. As you decrease the moles of gas, you're going to decrease the pressure that the vapor is exerting. Okay? Molecules with weak intermolecular forces readily escape to the gas phase, and we have a special word for those. It's called volatile. Right? If we say somebody has a volatile temper, it means they get angry easily. Well, volatile substances go readily from the liquid phase to the gas phase. Okay? So that's part of our conversation. The other part is this. As temperature increases, as we measure an increase in temperature, that means we have an increase in kinetic energy. Because remember, temperature is a measure of the average kinetic energy. So as molecules increase their kinetic energy, and sometimes what you'll see is a molecule like this. Again, remember, we have to learn to draw these things. So you might have a molecule like this and they would put kind of this like shaded region behind them to try to show them, how fast they're moving. So if that shaded region is very small, they're not moving very quickly, and if it's very long, that means that gas molecule is speeding along very, very quickly. So this would be a slow molecule, and this would be a fast molecule. All right, so just kind of a way to depict that in pictures. All right, so as the kinetic energy increases, you have more energy. You can break. That increase of energy can be used to start breaking intermolecular forces. And the more molecules that you would have then in the gas phase, and so vapor pressure increases. So your claim is that as you increase the temperature, you observe an increase in the vapor pressure. That's a claim. What you need for evidence is this. This is the evidence that supports that claim. All right? So let's take a look at a couple of graphs of this. Here are two graphs showing different substances. This is all of these are all hydrocarbons. Hydrocarbons are all non-polar. And so we're going here from pentane to octane. So this is a size issue. Don't say molar mass. You can kind of think it, but don't say it. Increase size, increase electron density, increase polarizability. You need to memorize this. I hope somebody wrote a song already for us. Increase polarizability. You're going to increase your strength of London dispersion. Okay? So if you take a look at a given temperature here, so let's just pick 60 degrees, and we go up to a given temperature, you notice that the one with the lower London dispersion has a higher vapor pressure than as you go to the one with greater. So we see in this direction an increase in IMFs. So we saw a decrease in the vapor pressure. Okay. Now, you also notice that in general, as temperature increased, the vapor pressure increased for every one of them. Okay, so that's true across the board. Now, the other point I want to make here is this line right here. When all of these are boiling points, all right, every single one of these could be considered a boiling point. So if we were looking at a phase diagram, pressure versus temperature, and we were looking at a phase diagram, these are graphing this portion of your phase diagram. So all of these are boiling points, but when we are at atmospheric pressure, when we are at 1 atmosphere, these are all called the normal boiling points, as opposed to all those abnormal boiling points. Okay, normal boiling point. All right. So that is a little bit about those. Now let's compare substances of a little bit different type of comparison here. In this other graph, we have water, which can hydrogen bond. We have ethanol that also can hydrogen bond, but I think I'm going to make a good point that its hydrogen bond is weaker. Then we have diethyl ether, which is dipole-dipole. Ethylene glycol can also hydrogen bond, and it's much stronger than water because there's ethylene glycol has, if I remember, it's got a bunch of OHs on it. I'm not going to remember its structure, all right, for ethylene glycol, but it has a number of, this is glycerol, I'm pretty sure. It's been too long since I've taught organic. Okay, so it's got a number of OH groups that can hydrogen bond, which makes it stronger than water. So again, you notice with every one, as you increase temperature, you increase the vapor pressure. We see our normal boiling points here. But here's the point that I wanted to make is, and I can't even come to a line where they intersect except way down here, right? You notice here that as you go to the weaker IMFs, so as you decrease the strength of the IMF, you increase the volatility and you increase the vapor pressure. Now, looking at the structures, you might not have guessed this, but if I gave you this data, you should be able to tell me based on this higher vapor pressure. Look at the order of their vapor pressures. So if you look at the order of the vapor pressures, it's ethanol. I'm just going to call that ETOH. The ethanol vapor pressure is greater than the water vapor pressure, which is in turn greater than that ethylene glycol. And based on that data, you should be able to tell me that the intermolecular forces of these would go in the opposite direction. Okay. Now, another quick couple of... No, I'm going to end it now. And we will finish up one more video in this series. So until then, this is signing off.